this set of notes, we're going to continue talking about different types of estimators and properties that we would like estimators to have. So remember that we can use a sampling distribution of a statistic to help us decide whether or not that statistic is a good estimator of a parameter. And then further, recall that theta hat is an unbiased estimator if its expected value is equal to theta, the parameter we're trying to estimate. So unbiased is a good property for an estimator to have. We would also like it to have minimum variance. So we're going to start out by talking about the idea of relative efficiency. So it's usually possible to come up with more than one unbiased estimator for a given parameter of interest. And so for example, if we wanted to estimate the population mean and we had a distribution that was symmetric, we saw earlier that both the mean and the median are unbiased estimators. So given two unbiased estimators, and we're going to denote them as theta hat 1 and theta hat 2 of some parameter theta, and we've defined our variances here respectively, the efficiency of theta hat 1 relative to theta hat 2 is denoted by the efficiency of theta hat 1 theta 2 and is denoted here by this ratio. So the question here is, what does efficiency tell us? So notice if the efficiency of theta hat 1 theta hat 2 is greater than 1, then what that tells us is that the variance of theta hat 2 is greater than the variance of theta hat 1. So in this case, theta hat 1 would be more efficient. So it gives us a way to compare the variances, and not only we'll be able to see, which one's larger based on whether or not the ratio is greater than or equal to 1, but we can also, looking at that ratio, understand how much larger. So for example, suppose we want to estimate the mean of a normal population. We know the population mean is equal to the population median because the normal is a symmetric distribution, so it makes sense to consider the sample mean and the sample median as both estimators. So consider the following. We're going to let theta hat 1 be equal to the sample median, and we're going to let theta hat 2 be equal to the sample mean. So we know the variance of theta hat 2, we've talked about this before, and we know that that's equal to sigma squared divided by n. And then we could show the following. The variance of theta hat 1, or the sample median, is equal to 1.2533 squared sigma squared divided by n. So we can calculate the efficiency. Or I should say the relative efficiency. So we have the variance of theta hat 2 over the variance of theta hat 1, and we get the following. Okay. So in other words, what that tells us is the following. So theta hat 2 is more efficient at estimating mu when the data are normally distributed. And so this gives the argument of why, if we're estimating the population mean, one of the reasons we want to use the sample mean to estimate it. So let's look at another example. Let y1 through yn be a random sample from the uniform distribution on the interval 0 to theta. And we're going to look at two different estimators of theta. We're going to look at 2y1 and 2y bar. So the first thing we're going to do is we're going to show that these two estimators in question are unbiased. So notice first that at mu, which is equal to the expected value of y, is equal to theta 1 plus theta 2 divided by 2 for a uniform distribution, which in this case is just going to be equal to theta over 2, because we are looking uniform on the interval from 0 to theta. So theta 1 is 0 and theta 2 is equal to theta for this example. And then further, we could find the variance for this distribution using the properties of a uniform distribution. We know that this is equal to theta 2 minus theta 1 squared divided by 12, which is just equal to theta squared over 12 for this particular uniform distribution. So let's find the expected value of our two estimators. We have the expected value of theta hat 1, which is equal to the expected value of 2 times y1, which is equal to 2 times theta over 2, which is equal to theta. So the first estimator is unbiased. And then we could look at the expected value of theta hat 2, which is equal to the expected value of 2 times y bar, which again is equal to 2 times theta over 2, which is equal to theta. So both of these are in fact unbiased. Now let's find the relative efficiency. So we need to find the variance of each. So first we're going to find the variance of theta hat 1. We'll notice the variance of theta hat 1 is equal to the variance of 2 times y1, which is equal to 4 times the variance of y1, which is equal to 4 theta squared over 12 based on what we looked at above. So we get theta squared over 3. And then we could do the same thing for the variance of theta hat 2. And you can show that this is equal to theta squared divided by 3n. So next we can find the relative efficiency. And again, that's going to be equal to the ratio of the variance of theta hat 2 over the variance of theta hat 1, which is equal to the following. So notice that 1 over n is less than 1 if n is greater than 1. So in this case, theta hat 2 is more efficient when we have a sample size of 2 or greater. So when n is equal to 1, notice that theta hat 1 is equal to theta hat 2, because if you only have a sample of 1, y bar is just going to be equal to the single observation. But when n is greater than or equal to 2, we have that theta hat 2 is more efficient. And if we look at what's going on with these two estimators, that makes sense. Notice that our first estimator here is only using a single data point, whereas this estimator would be using all of the data points. If we want to reduce our variability, it makes more sense to look at all of the data points versus just the first one. Next, we're going to look at what is called the Row Inequality. So suppose that we have y1 through yn, iid, with probability density function f of y, which has the parameter theta in it. If theta hat is an unbiased estimator of theta, under some very general conditions, we can show that the variance of theta hat is greater than or equal to what's called the information function, and the information function is defined here. So if the variance of theta hat is equal to the information function evaluated at theta, then what happens is we automatically know that theta hat is what we call efficient. In other words, it's going to have the smallest possible variance among all unbiased estimators. So this is one way that if we have an estimator, we want to show that it's efficient. What we can do is if its variance meets the Row Inequality lower bound, we know that it is an efficient estimator. Next, I just have some properties of the ln function, just kind of a reminder if it's been a while since you've worked with those. So next what we're going to do is we're going to suppose that y1 through yn are IID exponential with mean theta, and we're going to consider the sample mean as an estimator of theta. And so our question is the sample mean an efficient estimator of theta? And we can show this by using the Kramer-Rao lower bound. So as an example, we're going to see what happens. Alright, so first of all, let's recall if we have an exponential random variable, then we have the following. So the first thing I'm going to do, if we go up and look at the Kramer-Rao lower bound, notice that one of the things I'm going to need is the ln of f of y. So that's the first thing that I'm going to find. And then notice we can show that this is equal to y to the theta minus 1 minus the natural log of theta. Alright, so the next thing I'm going to need, if we go up and we look at the information function, so we just found the natural log of f of y, well notice what else I'm going to need is I'm going to need the second derivative. So now we're going to find the first and the second derivative of the natural log of f of y with respect to theta. So first we're going to find the first derivative. Okay, and then notice this is equal to the following. So there we have our first derivative. So next we're going to find our second derivative. And then notice this is equal to the following. Okay, so we found the natural log of f of y, we found the first derivative, and we found the second derivative. So now let's go back up to our information function. So in other words, we have found this whole piece here, but notice our next step is we need to find the expected value of that piece. So let's do that next. So next, we have the expected value of negative the second derivative of the natural log of f of y. So that's going to be equal to the negative expected value of negative 2y theta over 3 plus 1 over theta squared. So remembering that theta is a constant, we get the following. Let me change that here. We're going to bring the expected value in. So I went 2 times the expected value of y divided by theta cubed. And again, this is because theta is a constant, is why we can do this. The only piece that's random is the y. Now we need the expected value of y, but we know that y is distributed exponential with mean theta, so therefore we know the expected value of y is equal to theta. So this is equal to the following now. So notice, oops, that should be a theta 3 there. So notice in the numerator here that theta is going to go away and that is going to become a 2. So now we have this is equal to negative 2 over theta squared plus 1 over theta squared. And so this is going to become 1 over theta squared. All right, so now going back up to the information function, notice that we have found this expected value, so the only thing we need is to divide 1 by that number times n. So last, we have the information function evaluated theta, which is equal to, and here I'm just going to write down the formula for good measure, I just realized I forgot the theta squared there. Okay. So all over 1 is going to be equal to 1 over n times 1 over theta squared, which is equal to theta squared over n. So we have the information. So now the whole reason we're doing this is we want to show that y bar is an efficient estimator. So if we can show that the variance of y bar is equal to theta squared over n, then we know that y bar is an efficient estimator because it reaches the Kramer-Rao lower bound. So now consider y bar. Okay? We know that y bar is unbiased. We know the expected value of y bar is equal to mu, which is equal to theta. So y bar is unbiased for theta. And then we also know the variance of y bar is equal to sigma squared over n, which for the exponential distribution is theta squared over n. So the Kramer-Rao inequality states that if theta hat is an unbiased estimator, so we have that because y bar is unbiased, and if the variance of theta hat reaches the Kramer-Rao inequality lower bound, then it's efficient. So since the variance of y bar is equal to sigma squared over n, which is theta, go back here, which is theta squared over n, since this value is equal to the information function evaluated at theta, then we know that y bar is an efficient estimator. So what this tells us is for the exponential distribution, y bar is the best estimator of theta that can be found. You know, we could maybe find a different estimator, but it wouldn't necessarily be better. This one, y bar, is the best estimator that we could find. We might be able to find another one that is just as good, but we're not going to find another one that's better. So another property that we might want to talk about when it comes to evaluating estimators is the idea of consistency. So consider tossing a coin n times. We estimate the probability of a heads by p hat equals y over n, where y is the number of heads that occur. So don't automatically assume that this particular coin is a fair coin. So as n gets larger, we anticipate that p hat, which is equal to y over n, should get closer and closer to true value of p. So let's suppose that we do have a fair coin. So notice for a fair coin, we know the probability of heads is right at 0.5. So we have both of these here. And so we could look at a single estimator that we have on the left, and we can see over time it reaches 0.5 in a single sample. Or we could look at multiple samples, and we see that over time, even for multiple different samples, using that same estimator, we do get closer and closer to the 0.5. So in particular, the error of estimation, which we define to be theta hat minus theta, for this example is equal to p hat minus p, we expect it to get smaller and smaller and smaller. So in particular, if we consider any value of epsilon greater than 0, where epsilon greater than 0 is just some small number that's not equal to 0, then what we're saying is the probability that theta hat minus theta less than or equal to epsilon, which for this example is the probability that y over n minus p is less than or equal to epsilon, should get closer and closer to 1. So looking at this probability statement, notice that the only random piece here is the estimator. So really what we're saying here is the distance between the estimator, the random piece, and then theta, which is the piece we're trying to estimate. What we're saying is that it should get closer and closer and closer to epsilon. In particular here, so notice we have n involved, so we're saying really as n gets larger, we expect this to get closer and closer to 1. So let's look at using y bar to estimate mu. So remember that the expected value of y bar is equal to mu. And the variance of y bar is equal to sigma squared over n. So when we look at the sampling distribution of x bar, I should have said y bar, not x bar a second ago, we have that the variance, sigma squared over n, decreases as n gets larger and larger. Now recall that the error of estimation is the following. So as n gets large, we would like the error to get small. So in particular, we want the following. We want the limit as n goes to infinity, the probability that y bar n minus mu less than or equal to epsilon is equal to 1 for all possible epsilon that we could define. And so where this is going in terms of our sampling distribution is, one way to think about this is for a small sample, the sampling distribution of y bar might look like this. Whereas as n approaches infinity, what's going to happen to that sampling distribution is it's going to become closer and closer to mu, because the variability is decreasing as n approaches infinity. So when we think of in terms of the probability that the y bar, the distance between it and mu, as our sampling distribution, that variability decreases and decreases, we can see that the probability of the distance between y bar and mu, the probability that is within some small amount is going to increase and increase until it gets to 1, and this is contingent on n going to infinity. So in other words, our sample size is just becoming massive. And so this motivates our definition of what it means to have a consistent estimator. The estimator theta hat n is a consistent estimator of theta if for all epsilon greater than 0, as n approaches infinity, the probability that that distance between theta hat and theta, so again theta hat being the random piece, being less than just some epsilon is going to approach 1. And again, it's the idea that that sampling distribution, its variability is decreasing as n increases, so you can almost think of that sampling distribution as just compressing towards mu is one way to kind of think of that. And so equivalently we could have this statement right here. So recall Chebychev's theorem, which says the following: let y be a random variable with finite mean mu and variance sigma squared. Then for any k greater than 0, we have the following. Notice that these look very similar. So we could show that if theta hat n is an unbiased estimator of theta, then theta hat sub n, and so this is an estimator that depends on the sample size, for example the sample mean, is a consistent estimator of theta if that variance approaches 0. And we can see that for the case of y bar. So let's do that. So we've already shown many times that the expected value of y bar is equal to mu, so we know that it's unbiased. And then also we know that the variance of y bar, which is equal to sigma squared over n, so if we look at the limit as n approaches infinity of the variance of y bar, we can see that that's equal to the limit as n approaches infinity of sigma squared over n, which obviously equals 0. So then by the theorem, y bar is a consistent estimator of mu. And so this result is called the law of large numbers, and you probably heard of that in your intro statistics course. So we got some more definitions here. If theta hat sub n is a consistent estimator for theta, then theta hat sub n converges in probability. So saying that an estimator converges in probability to a parameter is the same thing as saying it is consistent. So let's look at another example. Let x1 through xn be IID with the expected value of xi equal to mu1 and the variance of xi be equal to sigma squared over 1, or probably sigma squared 1, which is less than infinity. And then let's look at a second sample, y1 through yn, which are also IID, but now all of them have expected value mu2 and variance sigma 2 squared. We're further going to assume that the x's and the y's are independent. So we are going to show that x bar minus y bar converges in probability to mu1 minus mu2. In other words, we're showing that x bar minus y bar is a consistent estimator of mu1 minus mu2. So the first thing we're going to do is we are going to show that it is an unbiased estimator. So we have the expected value of x bar minus y bar. We know that that is equal to the expected value of x bar minus the expected value of y bar, which is equal to mu1 minus mu2. So therefore, x bar minus y bar is an unbiased estimator of mu1 minus mu2. Okay, next we need to look at the variance. So we have the variance of x bar minus y bar. Well, that is equal to the variance of x bar plus the variance of y bar, which is equal to sigma 1 squared over n plus sigma 2 squared over n, which that is sigma 1 squared plus sigma 2 squared over n. So next we're going to look at the limit. So the limit as n approaches infinity of the variance of x bar minus y bar is equal to the limit as n approaches infinity of sigma 1 squared plus sigma 2 squared over n, which is obviously equal to 0. So again, by the theorem above, x bar minus y bar is a consistent estimator of mu1 minus mu2. So in other words, we're saying that x bar minus y bar converges in probability to mu1 minus mu2. Right. Here is a useful theorem in terms of convergence in probability. So suppose that we have two estimators. We have theta hat n and we have gamma hat n. And suppose that theta hat n converges in probability to theta and that gamma hat n converges in probability to gamma. Then what we can do is we can look at several functions of theta hat n and gamma hat n and determine their convergences in probability. So for example here, in part A, we look at theta hat n plus gamma hat n. We see it converges in probability to the sum of the two parameters. Similar when we look at subtraction, multiplication, and when we look at division. And we could even look, and then further, if we know that the square root of theta hat n converges in probability to the square root of theta, then this only holds if the probability that theta hat n is greater than or equal to 0 equals 1. Again, we got to be careful with negative signs there. And then also if g is a real valued function that is continuous at theta, so we do need that continuous at theta, then that function converges in probability. When we apply that function to the estimator, it converges in probability to that function applied to the parameter. So we can use this to help us with that previous example we just looked at. So we know by the law of large numbers, since the variance of xi, which is equal to sigma squared, is less than infinity, and the variance of yi, which is equal to sigma squared, or sigma 2 squared, is less than infinity, then we can show that x bar converges in probability to mu1 and y bar converges in probability to mu2. So therefore, using the theorem above, and we're using part A, we get the same thing that we just did on the previous page. So this theorem is really handy when it comes to showing that something converges in probability, especially when it's a function of multiple random variables. All right, the last thing we're going to talk about is sufficiency. So up to this point, we've chosen statistics based on intuition, and we've also shown that y bar is a better estimator than estimators like y1 plus, oops, that should say a y2 there, which do not involve all of the values of a random sample. So we looked at that example just a few minutes ago where we looked at that uniform distribution and we compared y bar versus just using the first observation y1, and we see in general it's better if we use more of the data. This is true because when we only use, for example, y1 and y2, we're using some valuable information from our samples. So do estimators like y bar and s squared lose any valuable information about the parameters mu and sigma, or are they what we call sufficient statistics? So in other words, if we don't lose any of the information, then we know that we have a sufficient statistic. So let's look at kind of a motivating example here. We're going to let y be distributed binomial in P, and we're going to say that x1 through xn are IID binomial, and we're going to let y be equal to the sum of the xi. Is there a sufficient statistic for P, or have we lost any information by reducing the x1 through the xn to that one number, y? And remember here that those x's, we could say they're binomial 1p, or that's the same thing as a Bernoulli random variable. All right, so consider the following. So consider the probability that x1 is equal to little x1 all the way out to xn is equal to little xn, given that y is equal to y. Now we can apply our definition of conditional probability, And we know this is equal to the probability that x1 is equal to little x1, dot, 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 xn is equal to little xn, comma, y is equal to little y, divided by the probability that y is equal to little y. So now let's consider the numerator. So we're going to look at the probability that x1 is equal to little x1, xn is equal to little xn, and that capital Y is equal to little y. But notice this is equal to the probability that x1 is equal to little x1 all the way out to xn is equal to little xn. In other words, we can drop the y equals y, and the reason for that is as long as the sum of the xi's is equal to little y. In other words, we haven't lost any information there. If I know what all the little x's are, I know what y is. So these two probability statements are the same. Now further, we've assumed that the x's are independent from one another. So notice this is equal to the following. Okay, so now let's actually substitute in what these probabilities are. So we know that the probability that capital X is equal to little x is equal to p to the x1, 1 minus p to the 1 minus x1. And again, this is because these are distributed binomial 1p, or you could just say Bernoulli 1p. And then we have p to the xn times 1 minus p, 1 minus xn. And then we can use our properties of exponents here, and notice that this is equal to the probability from the sum I equals 1, not the probability, I'm sorry, p to the power of the sum I equals 1 to n xi times 1 minus p to the power of the sum I equals 1 to n 1 minus xi, which is equal to the following. Okay. But remember that by definition, the sum of the xi's is equal to y. So we have that up there at the top. So this can now be written as p to the y, 1 minus p to the n minus y. And again, this is as long as the sum of the xi is equal to y. And so we've defined that up at the top. So let's go back to that original probability that we were interested in other words, this one right here. We just found the numerator, so now let's write out what that probability is. So we have the probability that x1 equals x1, comma, dot, 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 xn equals little xn, given capital Y equals lowercase y is equal to p of y, 1 minus p to the n minus y. And then notice in the denominator we have the probability that capital Y is equal to little y. Well, we know that y is distributed binomial in p, so we could just write out using the PMF. So we have n choose y, p to the y, 1 minus p to the n minus y. And notice this is equal to n choose y to the minus 1 as long as the sum of the xi is equal to y. So what the important part, what this tells us is the following. This probability does not contain any value of p. So we say that the y, which is equal to the sum of the xi's, is sufficient for p. So in terms of the binomial, what we're saying is if we look at our sample information, and we've got a series of successes and failures. By looking at the sum of those, the only thing we've really lost is the order in which the successes and the failures occurred. But that order really does nothing in terms of estimating the parameter p. So by using y bar, we've lost that information, the order that they occurred, but we haven't lost any information about p. And so that's why we say that y, which is the sum of the xi's, is a sufficient statistic for p. So here's the idea. If you know the value of y, you don't get any more information about p from if you look at the individual successes and failures. So therefore y is a sufficient statistic for p. Now to actually estimate p, we actually use a function of y, which is p hat y over n. So here's our definition of a sufficient statistic. So let y1 through yn denote a random sample from a probability distribution with unknown parameter theta. Then u, which is some function of y1 through yn, or some function of the sample, is a sufficient statistic if the conditional distribution of y1 through yn given u does not depend on theta. So let's refer to that previous example where y was distributed binomial in p. Now let's let x be equal to x1 plus x2, in other words, just the first two, and the question is t a sufficient statistic? So before we even show this, keep in mind here, we're only looking at the first two, success and failure. We're ignoring the other n minus 2 pieces of information, which are obviously going to contain information about p. So just intuitively, we should know that we are going to find that this is not sufficient. But let's see how we can actually do that. So the first thing to note here is notice that t, my statistic, is distributed binomial to p. So we're going to consider that conditional probability. And then again, just like we did before, we're going to apply the definition of conditional probability. Okay. Now again, just like before, we're going to focus on that numerator. And here, we're going to use pretty much the exact same steps that we used before. Notice if I know what the first two are, then I know the sum of the first two, so this just becomes the following. And then we can apply independence. And then we can use, since each of the xi's is distributed binomial 1p, we get the following just like before. Okay. Also, we know the following. The probability that t is equal to little t is equal to 2, choose t, p to the t, 1 minus p to the 2 minus t. And again, this is because t is distributed binomial to p. So now we can fill in that conditional probability that we have up above, the one that we're really interested in. So the probability that x1 equals little x1, xn is equal to little xn, given t is equal to little t, that's going to be equal to the following. then this becomes so we've got 1 over 2 choose t, p to the sum of the xi minus t, 1 minus p to the n minus the sum of the xi minus 2 plus t. Now, since t is equal to x1 plus x2, we can show by what we just had that probability, the x1 is equal to little x1, xn is equal to little xn, given t is equal to t, is equal to the following, which is a function of p. And so since that probability does contain the values of p, we see that t, which is equal to x1 plus x2, is not sufficient for p. And again, that makes intuitive sense that if we just use the first two elements of the sample, we're not going to have a sufficient statistic. So how do we find sufficient statistics? Well, in order to do that, we do need a little bit of new notation, and we're going to use this new notation actually in the next module as well. So suppose that y is a discrete random variable and p of y has parameter theta in it. We emphasize the following by writing this right here instead of just py. Similarly, for continuous random variables, we could write f of y given theta. So it would be handy to have one symbol so we don't have to keep writing everything for these two cases, in other words, the little p and the f. So if we let y1 through yn be random variables, the likelihood function is given here. So all of this is what we call the likelihood function. And so if you consider discrete random variables, then the likelihood is equal to the following, and then similar for continuous. So the factorization criteria is another way to help us find sufficient statistics. If we let u be a statistic based on the random sample y1 through yn, then u is sufficient if and only if the likelihood can be separated as the product between one function that depends on u and theta and one function that only depends on the rest of the sample. And so we can redo that binomial example that we just looked at by using the factorization criterion. It makes it a little bit easier. So recall for this example, we had that the x1 through xn were IID binomial 1p, and that y was equal to the sum of the xi was distributed binomial np. So let's write out what our likelihood function is first. So our likelihood function of x1 through xn given p was equal to the following. And we're getting this by applying this piece right here, because remember that p of y given theta was equal to p to the xi, 1 minus p to the 1 minus xi, and then what we're doing there is by the independence, we're multiplied them all together, just like we did in the previous example. So here, we're going to let u be equal to the sum of the xi. I should be better here on my summations. Alright, so we are going to let g of u and p be equal to p to the u, 1 minus p to the n minus u, and then we're going to let h of x1 through xn be equal to 1. So notice that the likelihood here is equal to G UP times H of x1 through xn. So by the factorization theorem, y is equal to the sum of the xi is sufficient for p. Now the other way to pose this problem, if we hadn't looked at the x1 through the xn, let's say that we just looked at y, which we know is distributed binomial p. Notice there you would have the n choose y at the beginning of your PMF. Well, that n choose y could just be in the h function, and you would still end up with the same thing. All right, and so that is going to end this note set.